Thank you everyone for joining us today for September webinar. Today we have Balaraju Battu speak to us today. It is great pleasure to have him. I'm going to briefly introduce him to you. Dr. Battu is currently a postdoctoral associate at the AI and Data Science Lab at NYU Abu Dhabi. Before moving to NYU, Dr. Battu was a Max Weber Fellow in the Social and Political Science Department at European University Institute, Florence, Italy. He obtained his PhD in cognitive science at the Center for Behavioral and Cognitive Sciences at the University of Allahabad. His research interests are the evolutionary dynamics of cooperation and social norms and human-machine collective interactions. Today, he will talk about his recent research on evolutionary dynamics of cooperation, titled "A Few Bad Apples Can Destroy the Reciprocal Nature of the Majority." Please join me welcoming Dr. Battu. And Dr. Battu, please take the floor.
Thank you very much for a kind introduction. It's very nice to me to joining all these people. I was waiting for somebody. Generally, I did not get a chance to meet so many agent-based modeling people. I think some will be there. You can ask questions during a presentation after. I don't have many slides, only 17. Therefore, I can go slow. You can interrupt me whenever you want. Yeah, this project actually try to combine the cooperation problem with the social norms. I try to connect them. I studied cooperation during my PhD. Now slowly adapting the cooperation, understanding cooperation using social norms. In that, yeah, big project, this is one of them. Let's start. The presentation follows this way. I first explain what is the problem of cooperation. Generally, we use cooperation to study public good games. And we look at the repeated games, what's going to happen. Then there is a proposal, norms as a solutions. I see really norms going to norm going to solve the problem. And we see that norms need some kind of help. The norms itself doesn't solve the problem. We need some cultural leaders, then introduce the cultural leaders into the system. Then we see how these leaders might be good or bad, how these leaders influence the dynamics, and see how the norms influenced by these people. We know this from Tragedy of Commons from Hardin, 1968 essay in Science. The key problem, the key logic in Tragedy of Commons, like when each individual competing to maximize the slice, what they do is eventually they minimize the total pie that we see in the congestion, in the traffic, or any commons we see it. Yeah, that's if everybody try to short term, they try to maximize their benefits, the long run they're going to reduce the common benefit of all. Then how can you solve this problem? This is a big problem for many, many years, and many intervention solutions available to us. And let us see. This tragedy of commons also, we can formulate a game theoretic problem by using a public goods game. This is a public goods game. Generally, public good game, everybody given equal endowment. They ask them to contribute to the common pot. After everybody made donations or their decisions, what you do is you multiply the collected money and divide equally, irrespective of anybody contributed or not. We can see that the free riders gains higher payoff. The payoff, they get it from initial endowment and also common pool. If every individual think rational and selfish, he thinks also other also rational and selfish, the trivial solution for this problem is defection or free riding. That's what economic theory sees this problem that way. But if you run the same game, like a public good game, repeated interactions, you see so many different things than those things you can't look when you look the system in an economic perspective. Left side panel, you see the top left, you see that is the typical public goods game, run 11 rounds. The interesting thing about this experiment, if you see the initial round, there are a lot of cooperation, almost 45% people, they're donating the environment, but slowly it goes down because somebody observed that somebody free-rided in the beginning round, they will withdraw their resources, slowly it go down. I think this problem everybody knows about it. And some researcher tried to look at actually what type of people is in there in the system. The graph left side down, it shows the different type of people generally in this kind of repeated public good games. If you see the graph, majority of them act like a conditional cooperators. Conditional cooperator means they want to make a decision, depends on some critical number of people, they make decision before them. That type of people are more in the system than the normal just free riders or altruists, always cooperate or unconditional free riders. They're the minority. Majority of them are conditional cooperators. This view actually gives us the hope to solve this problem. If everybody is rational, selfish, you can't solve it unless very stern punishments. If the people are conditional cooperators because their decision depends on what happened in the previous round, this allows us to introduce norms and also other mechanisms that try to exploit the conditional nature of the cooperation. Most of my work is based on exploiting the conditional nature of the cooperation. Let us see what the literature says. These are the typical solutions you find it. One is altruistic punishments, a repetition. These two actually came from the Eleanor Ostrom work, Governing Commons. She introduced mutual monitoring as like a small commons in villages and many developing countries preserving forests and water resources. They use this mutual monitoring. The stylistic experimental version of it is altruistic punishments. Altruistic punishment means when the people play the game, after each round of the game, people have option to punish the free riders who are not donating to the common pool. It's many experiments have shown that many people are willing to pay some cost to punish the free riders. If the altruistic punishments are possible, actually you can build the cooperation. This is a very standing mechanism. Still, open question is why nature selection likes altruistic punishments, why they evolve. There are some answers available, but still is an open question. Another one is reputation. Like you play the game, after the game is over, you know who contributed, who not contributed. And on top of this public good game, you attach the indirect reciprocity. Indirect reciprocity works on donating to the positive reputation individuals and withdrawing the cooperation from the negative reciprocity individuals. This is like it is punishment, but indirectly. That means you are after public good game, you playing the indirect reciprocity. There you know the individual reputation, what he did in the common pool, that use information to cooperate or not. This also solve the problem. Exploiting the conditional nature of cooperation, this is what I did most of the time. What I try to do is in the agent-based models, I try to see that is there any way to create a critical number of cooperation each round, such a way that you can build the cooperation. All my research is based on this, creating some critical number of cooperation each round that help you to cooperation progress. And also along this one, in the literature, we know cooperation started using Prison's dilemma a lot. The Prison's dilemma, the standard problems, they solve it by thinking the individuals are rational and selfish. Still, they try to find out what are the conditions these people can cooperate. All the mechanisms have this kind of nature. Cooperation thrives when current costly actions yield future rewards. If there are future rewards for current actions, the direct reciprocity or network reciprocity, all the mechanisms are based into this category. But direct interactions, the Prison dilemma assumes individuals are selfish and rational, but that is not true when you do the experiments. Let us see here. Here, to solve the cooperation problem, I try to use social norms. What are the social norms? Social norms, mostly the literature became very popular due to the Christiania Beccari. She came with measuring the social norms. She got a definition that operationalizes and you can measure in the field or experimental laboratory. that drive this social norm literature, or the research in really so much progress in last decade or so. Before that one, it was like a sociology, but there are not much clear measurements. According to Bikeri, there is if some behavior or become a social norm only if the two conditions met. One of them is called empirical expectations or normative expectation. Empirical expectation about suppose I'm in the group, what kind of behavior I frequently observe, that drives me, that is about empirical expectations, or what I expect what group members should do. That's the empirical expectation. Normative means what group member think what I should out to do. The second expectation actually leads to the punishments or enforcement. The first one just drive can I cooperate or can I do certain action or not, driven by the first expectation. Empirical expectation only drives to make a decision to make or not. The normative expectation actually stabilizes the certain behavior. That's what I found in my simulations also. As we said it, in the public good games context, people behave like conditional cooperators. Therefore, because norms are based on expectations, therefore, by changing these expectations, actually one can change the behavior. Therefore, social norms provide a causal mechanism to understand the behavior. That's a good thing about it. Here, I'm going to use evolutionary game theory. I think everybody familiar with it. In evolutionary game theory, the payoffs are equated with the fitness. That is a transition we make due to the Maynard-Smith. To build any evolutionary game theory models, you need to have 4 ingredients. One is the population required. These populations have a behavior or strategies, and obviously they reproduce. They pass on certain behavior to next generation. When the passing on next generation or reproduction, there is a mutations or miscopying. People also learn, or the strategies which are giving a higher relative payoff, they will, or fitness, they will proliferate in the population. In the cultural evolutionary literature, we see as a selection as a social learning. People try to copy the successful individual strategies in the social learning. Here, I try to show that this only model I have it in the whole presentation. If left side, if you see it, these I created what is going to happen in the public good games by the setting certain parameters. Here, I took a population size 100, and each individual have a sub threshold value. That threshold value, like a CE, conditional expectation, that is the expectation people get into the public good game. They look at the previous cooperation level. If the previous cooperation more than the individual expectation, the agent more likely to cooperate. That's where I define the conditional cooperation in the model. To account for the certain noise, I build the probability function. This probability function function of number of cooperative actions took place in the previous round, or amount of cooperation, and my individual threshold value, CI. This difference is modulated by beta factor. By changing a beta between 0 to infinity, I can make probability higher and lower even with the same difference. If a beta is 0, that time my PI become a 1.2. That means people are making decision by coin tossing. In that case, people are not access to how many people cooperate in the previous round. If beta is infinity, that means my decision only depends on the sign. That means if my threshold value less than the previous amount of cooperation, I just cooperate. The beta value between 0 to 1 or 0 to 2 interesting. That makes this probability function like not a step function, but a smoothly varying function. Only have these ingredients. I have a population, they're born with a certain conditional expectation values. In this case, I consider population 100. That means from uniform distribution, I attach each number for each individual. For example, CA equal to 0, that means the individual always cooperates. If CA equal to n, that guy never going to cooperate into the system because he never observed more than n number of cooperative actions in the previous round. In between, they act like a conditional cooperator. Yeah. If you see go down, it's like a normal public good game, and these are normal things like after probability function pi I q, like a like what is the payoff you get from the public good. QI is the updating, how you update the strategy. Depends on the relative fitness, comparing relative fitness between two individuals. This standard procedure. If you look at the left side and right side you see these are public good games run across different countries. You see all of them goes down to close to zero if even start very higher. Actually, I can produce all of these graphs by changing my parameters left side by adjusting beta and cost. Actually, any trajectory I can get it. That means the method what I'm using it makes sense in context of public good games. You can ask any question this time because this is only the model in the whole presentation. That nothing's hidden thing. This is simple model. Or you can ask at the end of the presentation.
Yeah. Yeah. Can I ask a clarifying question?
Yeah, sure.
So the beta parameter. First of all, can you just explain the beta parameter again, and then I think I have a
beta parameter in physics. It is like a statistical mechanics. Beta equal 1 by kt. It's like an inverse to the noise. Or if you plot the probability function, it control the steepness of the function. If beta is infinity, it act like a step function. That means they only respond to the sign NC minus CEI. If the beta less than generally people look at what has happened between 0 to 2. In that cases, you can smoothly construct the probability function PI.
Okay, so then my question is the assumption here that people have perfect information about the number of cooperators and
you can interpret other way, like if beta is infinity, that means people have a perfect information about previous round cooperation level or how many people cooperate in the previous round. That is the meaning if beta is infinity. If beta is equal to 0, that means individuals no access to information what happened in the previous round. That case, they will either cooperate or free ride with tossing a coin.
Okay, thanks.
Yeah. Yeah. Now what I do is after each round of the game, I introduce the norms. There are several ways to introduce the norms. I'm using the standard procedure followed in many studies. What they do is, after the game is over, I pick up the two individuals at a time. One individual compare with the other individual action. If they both do the same action, suppose individual I compared with the individual J, if I cooperated, J also cooperated, I payoff bit increases. If I cooperated, J defected or free rided, I's payoff go down. That means I'm comparing. Am I doing the same action like what frequently observed in the system? That's it mean by this. If I free ride, let's say if I pick up other individual, also free rides, my payoff go up. If I'm free ride, the randomly picked individual is cooperate, my payoff go down. That's why I'm implementing the norms here. Because I'm randomly picking the two individual comparing, that means I'm trying to look at the frequently observed behavior in the population. I think somebody. Yeah, that's why I'm implementing the norms. This is another technical stuff in the model. If anybody needs clarity, I will explain it. Here, what I was doing after the game is over, I know what people did in the previous round. I know each individual is cooperated or defected or reciprocated or free-rided. Then I try to impose norms on these individual actions. If the two individual matches, round will pick two individual actions that matches. One of the individual get the payoff increase a bit high. He in this model I make the +1. If doesn't, it goes down -1 is payoff. Yeah, I do with each individual same thing. Then that means people got a payoff from the public good game, and also this matching mechanism also adds or subtracts some payoff from them. Yeah. Then you go for the updation of strategy. That's only the key ideas in the paper. If you do like everybody equal footages, everybody have equal preference, there are no hierarchy in the system, this is what's going to happen. Actually, you don't build the cooperation. It's you see it's below 40% even after imposing a norms in it. That means norms in this given system, not able to establish a cooperation. Then what I do is, we know that norms are really not really building a cooperation here. Therefore, I'm introducing some cultural leaders in the population. That means here cultural leaders means they generally in literature called stubborn altruists. These are some individuals, they don't change the behavior. Whatever happens in the population, they just stick to their behavior. For instance, I have two kind of people I introduce in the population. Some people like altruists, all the time they cooperate irrespective of what is happening around them. Another type is stubborn defectors or unconditional free riders. They never change their behavior, always defect. I try to see that how the intervention of these two people into the population, how they're going to change the norm. That try to see it. What is happening actually when you introduce the good altruists into the population, some critical number of them, we're going to see how many required. That generally in outside also we see that they trigger the good behavior, and also they involve in the norm enforcement. And also because if you there are a critical number of good people around you, that influence the learning also. These three things going to happen. It is the same happen with the bad individuals, same thing. Here the idea is the cultural leaders means the stubborn altruists. All the time they cooperate irrespective of whatever happening around them. They're unconditional cooperators. Similarly, we have a cultural leaders might be bad, they're unconditional defectors, unconditional free riders. Yeah, I try to see by changing this percentage in the population, I try to see how the dynamics are going to change. Yeah, here you can see the, let me move this. Here you can see the x-axis number of generations and y-axis cooperation level. If you look at the legend, all C, this is the number of percentage of cooperators. All see here, all the time they cooperate, stubborn altruist. I'm introducing them. The 0% means like a standard public good game, just with the conditional cooperators. Then I try to see that if you introduce 5%, 10%, 20%, 30%. That means in the population of 100, well, suppose if I say all see 5% means 95% of people are like normal conditional cooperators, 5% will be the unconditional cooperators. Then I try to see how the dynamics develop. What is the dynamic involved? You have public good game. After the game is over, you're enforcing a social norms by randomly matching two individuals. If they match equal action, the payoff increases. The action doesn't match, payoff decreases. That's what I'm doing when I enforce the norms. If you see here, even 10% can build around 70% of the cooperation level in the system. If you go more higher, obviously it increases more. This is what's going to happen. Here I just beta really doesn't destroy the cooperation unless to infinity. It just changes how fast, how slow the dynamics build up. It doesn't change really. If beta is very, very poor, beta is equal to 0, or beta is infinity, only these extreme cases, all only except beta is equal to 0, other values actually, you can still see the cooperation build up. If you see the next one, what it was, now in this given system, I try to introduce the unconditional free riders, or the people who all the time defective. Here we see the dynamics for keeping 20% of unconditional cooperators in the system, and try to vary the percentage of all D in the system. If I see already 5%, you can a previous graph, if you see, when the 20% is there, the cooperation will around 90%. Then it become almost 65%. If in the system you have a 5% of all the type, yeah. Obviously, 10% it goes much slower. That means even the population have some unconditional cooperators, and rest are conditional cooperators in the system. By introducing all the or unconditional free riders, I can pull the system down. That means cooperation goes down. That's what's going to happen. Here I drawn for various parameters what's going to happen. Actually, simulation ran for 20,000 generations. I took 5,000 and take average of it, I draw these graphs. The first, if you see the graph, top right, A in figure C, if you look at the x-axis, these are a percentage of all C in the system. And you see by different percent of all D, how the system goes down. If you see the 5%, 10% actually reduces the cooperation very high. The blue line is like a normal, without any all D in the system, only with the conditional cooperators and some fraction of altruists. That's the case. You can see that after 10%, even 5%, 60%, then later on it increases very high. What's going to happen here? And if you look at the B, here I change the cost, because the cost you put into the public good game, it does two things. One is it's costly for the individual who is cooperating. It also enhances the whole public good. In those cases, actually, free riding individual get the more payout. Therefore, if the cost is higher, obviously cooperation very hard to establish. Yeah. If in case of no free riders, obviously it's very high. But if you introduce free riders, that means the people who always stubborn, unconditional cooperators, they destroy the cooperation. Unless there is a very high number of altruists in the population. And graph C and D just try to look at how the beta parameter going to change the dynamics. Yeah. If you look at the beta parameter at 0, obviously it's yeah, cooperation level doesn't develop a lot, and if beta is equal to 0, that's almost 50%, because we have some mutations, and that will change. It will not be the same. But the other parameters, you can see that the beta will modulate the dynamics. On the right side, you see the same parameters are try to see introducing some unconditional free riders. They will pull the whole system down, except beta is equal to 0. When beta is equal to 0, obviously you see the cooperation level close to 50%. Here I try to look at what happened to the strategies, the conditional expectations. When I start the game, I use the uniform distribution 0 to n is equal to 100. Assign each value for each individual. That is the initial condition. But when I look into what happened to the strategy types, when you introduce altruists and the free riders, if you see in the blue, the bars in the blue is a histogram. If you see bars in the blue, obviously this become in all the game, the initial cooperation level I use the 50%. The game start with the 50%, because in a lot of experiments you see the more than around 50% people cooperate. That's why I took 50% as a 0th round cooperation level. Obviously, if this conditional expectation value less than 50, everybody cooperates. If you see the left side, when no unconditional traders are present, and all C 20%, you see the conditional expectations less than 50, very low values. That means all the individuals try to cooperate here. If I use the 10% of defectors, all D in the system, they push all strategies more than 50. Therefore, cooperation goes down. That's the reason it doesn't build up. Yeah. I show this same graph what I shown on before. Yeah. This tell you that that means in the given system, if the individuals behave like a conditional cooperators in the system, even you have some cultural leaders or stubborn altruists, by keeping few bad apples or unconditional free riders, they will destroy the cooperation. That's what I tried to show in this paper and research. What we can see, we can see to understand why this kind of results we got it. When you introduce altruists, they're doing two things. They're triggering the initial cooperation and also they're involving the enforcing norms. That's the reason you see the cooperation building up. That means the all C helping to build the cooperation by changing empirical expectations and also changing normative expectations. While we introduce the ALDI or free riders, they do the same thing, reduce the initial amount of cooperation, and also they reduce the punishments or enforcing norms. Therefore, you don't build the cooperation. These are the things we can think about. In human society, individuals often exhibit behavior. Conditional cooperative rather, yeah. The whole idea is the whole simulations and all this project based on when the people are conditional cooperators, that means their behavior depends on what they observe around them. That is a link with the empirical expectations. That means they're changing those expectations. That means creating enough amount of cooperation each level actually can build the cooperation. That's the idea behind it. If they are selfish, rational, you can't build the cooperation using this kind of mechanisms. Only punishments is the solution. But this one, you don't need a really very strict punishments. In the previous paper, what I published, there I did not use any punishments. There I tried to create some critical number of cooperation level each round using different mechanisms, and the punishments are rewards. Come to this talk, leaders can disseminate new empirical information, enforce norms, actively influence the cultural learning process. Their collective efforts contribute to the steering the population towards the desired behavioral shapes. Yeah, that's it of the presentation. You can ask any questions about model, assumptions I made, or any mechanisms behind it.
Thank you, Bala. If there's any question, please ask. You can raise hand and
Yeah, I'm trying to figure out how to operate the controls. You'd think I'd be good at this point. There we go.
okay.
Hey,
Hi.
thank you. So yeah, I was just I just had an extension that I was thinking of as you were going through this. What if I think I understood right that everyone, including the leaders, they're kind of stubborn in their positions, but they don't have particular more influence than anyone else, right? Could
Right,
you?
yeah.
So two ways I would think about extending would be one, that people aren't maybe looking at the whole population, but are looking at a certain subset of people, and leaders maybe have more connections or looked at by more people than others, or that there's some kind of weight on people's, I see one person defect, that tells me something, but when I see some respected person defect, that tells me something else.
Yeah.
I wonder if there's room for
yes.
playing with that, and whether you expect to learn anything from it. Yeah,
if we introduce those kind of things, actually, I think dynamics become much more faster. Actually, here, giving equal footage. Therefore, the influence of each individual is the same. Only thing is, because some critical number of good people, that introduces the initial cooperation level, and also you try to match more than if they're not present in the population. As you said it, yes, if you introduce a hierarchy or leaders, obviously leaders have more influence. They work in both ways, building a cooperation very, in a faster few rounds probably, and also bad leaders also destroy the cooperation much faster. That's for sure.
Mm-hmm. Very interesting. Yep. Thank you.
Here, another one. Yeah. Hi.
Yeah. So first, another clarifying question. When you were talking about the matching and norms and the payoff,
yeah,
there was basically a negative payoff if their actions were mismatched, and positive payoff if they matched. Is that right?
Right. Yeah.
So that means if they both defect, they still get a positive boost.
Yeah, it's suppose if you are a cooperator, let us say, and let's say in the given population, there's a majority of them cooperators. Therefore, I'm going to match with the guy who cooperated. Therefore, my action rewarded more. That's the idea. Yeah, when you do experiments, also people also do the same thing. Like Christiana Bicari experiments, what she does is, do you think this particular context, do you think which is the suitable action? If your action match with the majority of them, you will reward it. If not match with the majority, it will be penalized. That kind of idea I inbuilt into the system.
But so my question is, so that still happens for defectors? Like if majority of people are defectors, they match, they get.
Yes, it's happening with the defector also. That's the reason. If suppose I'm defected, in the given population, there are many cooperators. Therefore, I'm going to match with the cooperator. Therefore, I'm going to penalize. And it will be good if it's a defectors in the population. Therefore, yeah.
Well, I'm asking about if there's a lot of defectors and 2 defectors get matched, they get a boost for that?
Yes, they get a boost for it. Therefore, if you have more defectors in the system, it doesn't build up. The social norm not to be good or bad. It's like it depends on the conditional expectations. No, it's some societies build bad norms also.
Yeah, I'm curious what the actual proposed social mechanism is. Like if everyone's defecting and I get matched with another person who defected, why would we benefit?
That means, in that system, the defection free riding is the norm. That's it.
I know, but so is the imagined thing like I see somebody else also free ride and then I say like, good job, now we're going to share something? That seems sort of counterintuitive that 2 people defecting would then benefit each other somehow, as opposed to just no reward, no punishment.
Yeah, it's like the Christian behavior. Use one example. Let us say in a given system, everybody corrupted. If me corrupting doesn't look like a bad thing to do, that is a norm in the system. If everybody cooperated, me doing a bad thing, you look like a more bad.
Right, but if everyone's doing bad things and I do bad things, why would I get rewarded for that, as opposed to it just being?
Oh, because it's like rewarding means like I feel okay, nice. There are so many people like me. I'm also like them. That's a kind of psychological benefit you get it.
So this is not meant to be a material reward. It's just
you're I given right a number, but there's a paper NS Fair. It talks about psychic cost. Yeah, it's that also still a number, but yes, for calculation, I'm putting in the number maybe normal utility or cost due to the psychological. You are equating the people who are really or following the same thing or not. Yeah, okay. That's the idea.
Thanks.
Yeah.
Okay, any other question? Okay, great. So it's great to start new academic year with a relatively shorter webinar. So this is good. I think this should be a norm for our next webinars, because you tend to have like an extended time discussing, which is also good.
Yeah, probably I will add from this discussion probably what happened. Some individual influence more than other. Probably the number going to be much more less. You don't need many good people. Few is enough. They're influencing more. Similarly, very few bad people. They're influencing bad behavior. I will add that. Yeah.
Okay. Thank you, Balaraju, for such a great talk. It's a very interesting talk. And next webinar is October 4th, Wednesday. And here the Jacob Kelter will talk about advanced functions in NetLogo, and I really look forward to it. Thank you, everybody. Have a nice start of the semester. Bye.
Thank you very much for all of you and you all. Yeah.
Sure. Thank you.